So this is a problem where we've got an object, a rod, that's in the air and it's going to fall down and then land flat, sort of right here, right? And so the question is, what's the speed of the tip of the rod? So what's V right at this point? And so I'm going to approach this by, because we've got this full rod, what we can do is if we find omega, then from that we can find V, because that's R times omega. And there are different ways we can do it, but one of the easy ways is to do it using conservation of energy, right? I prefer that over forces if I can get away with it. And so conservation of energy, you have to be a little bit careful here because, we could say right here would be our U gravitational potential energy equaling 0. So that's fine. So then we would say it has some potential energy when it's at this point. And the place we find the potential energy, because different points along the rod are going to have different heights, we can remember that the center of mass is really useful. We can think about all the mass being located here. So we can think about this is the total mass, the middle is the center of mass, so we can say, we can find then this would be our initial point, okay? And so our energy initial would be equal to our energy final. Don't have any frictional losses. We don't need to take into account air resistance. And so we can say the initial is going to be U initial from gravity, right, which would be mgh, and our height is the height to the halfway point, right? This halfway point, this is whatever the length is, over 2. And then the final energy would be UG is equal to 0, and our kinetic energy, because we're looking at a rod that's rotating, would be 1/2 I omega squared. And that's the omega we can find. If we find that omega, we're going to find our speed. And of course, the speed at different points along this rod is going to be different. This is going to be the highest speed out here. Obviously, at the point, the pivot point, it doesn't have a speed. It's just staying there. So if we have somewhere along in here, it's not going to be moving quite as fast. But our initial kinetic energy, we're going to say, is 0 because it's starting from rest, right? Released from rest. So now, all we need to do is figure out what the moment of inertia is. So we look that up in our table. So we use our table, and this is a rod rotating about the end. So I for a rod about the end is 1/3 ml squared. And then we need the height. Well, this height is right here, h, and this is 60 degrees right in here. So it looks to me like h, we can get it by saying sine of 60 degrees is h over L divided by 2, right? Because that's the hypotenuse. And then we have the height, and we have this angle. So h is equal to L over 2 times sine of 60 degrees. So we plug that in here, and we equate these. We say energy initial equals energy final. And so we get mg, putting in for h, L over 2 sine of 60 degrees is equal to 1/2 ml squared omega squared. The masses cancel. I don't even need that. All I need to know is my length and put in my value of g. So my length is equal, I lost my 1/3. This happens a lot when you do these kinds of problems. You can lose terms, so please don't do that. So it's 1/2 times 1/3. So my L is 2 meters. And if I plug that in, that'll be 9.8 times 2 over 2 meters. So let's see, 9.8 meters per second squared times 2 meters over 2. That's easy math. Sine of 60 degrees is equal to now 1/6 L squared, which would be 4 meters squared, times omega squared. Notice the meters squared cancel out, and I'm left with per second squared, which works okay for omega. When I cross multiply everything, when I multiply both sides by 6 and divide by 4, right? So I multiply both sides by 6, and I divide by 4, so I can cancel this out, and then bring them over here. I get omega squared is equal to 12.7 per second squared. Now we can throw the radians back in to remind ourselves that this is an angular value. So omega now equals 3.6 per second, or 3.6 radians per second. Okay? To find the speed, because we weren't actually looking for omega, I mean we were, but the answer in the book is looking for our v, so we can plug this in here and say v is equal to r times omega, so v is equal to this radius out to the point that we're interested in is 2 meters, and our omega is 3.6 radians per second, or per second, so our v is 7.1 or 7.2, depends on your rounding here, meters per second. You keep all of the terms, you get a 7.1 meters per second. And so that gives you then your speed at the end. So we've used conservation of energy. We need to know the moment of inertia, of course, to find something that's rotating, and then we can find our final speed.